All right. So let's talk about inverse matrices for just a second. So first, remember a matrix is a function. So fundamentally, you have something like this. You have some space here. You have some matrix here. It goes to some other space over there, right? Here's a vector here, x. That vector goes over here to a vector called ax. You guys all with me on this? Okay, good. Now, let's suppose that we wanted to, I don't know, like do some algebra or shit. You guys ever have an occasion to do some algebra or shit? Is that like a thing that you guys have done? Surely I don't need to convince you all of the utility of being able to solve equations. Is that true? Ain't
I
never
think I
heard of.
might have done algebra in the past.
Yeah, I feel like all y'all probably have solved an equation or two. Some of those equations are probably easy. There are things like if you want to get if you want to get gravel delivered to your house, it's $75 a yard plus $150 delivery, right? So this is like your kind of cost of gravel, like cost of X yards of gravel is this. You all have done this problem. So there are two questions you can ask with this, which is how much does it cost for me to deliver 4 yards of gravel? Or how much gravel can I get delivered for $275? You guys familiar with both those questions? In the case that we had, how much gravel can I get delivered for $275? I would be asking this question, right? You guys with me on that? And then we want to solve for x, yeah? So to solve for x, we might do this thing where we like, oh, I don't know. I think you like subtract 150 and then divide by 75. Does that seem familiar? So that process is applying the inverse function, right? You're doing C inverse. And so you're going to get x's, whatever the hell C inverse is, done to, done to, not 75x plus, done to 275. You guys all on board with that process? Now, the case in which you wouldn't want to do simply subtract from 150 and then divide by 75 every single time is when you when you're automating this in a computer, right? And you want to just have a concise formula for it because you're going to do it 100 million times for each customer, right? Like you don't want to write down this equation every single time you have to do this. You want something like, x equals whatever formula of y. You guys all on board with that thought process? Okay, good talk. So that motivates me to want an A inverse that goes backwards. Now, this is a little bit obnoxious. I claim that you guys have some things that you think of as inverses that don't actually work. But we'll maybe talk about why later. For right now, I just want you to know that I want to construct an inverse function. So what I want is for A inverse to exist, right? And be a function. Now that's going to necessitate for some reasons that A be square. So we'll get into it a bit. I'm a little short, so I'm just going to throw this up there. So A square matrix A, which we'll assume is n by n, has an inverse B, also n by n, right? Because this is going to be Rn as a vector space over here, and this is going to be also Rn as a vector space. If BA is I is a B. We usually write right. B is A inverse. Everybody good with this idea? Ish? Okay. Let's do a quick example. Easiest example ever. 1, 0, 0, 1 has an inverse. What is it? What is the matrix that you can multiply on either side by this one to get the identity matrix?
Would it be 0, 1, 1, 0?
Let's think about that. So 0, 1, 1, 0. Maybe. Okay, so if I'm going to call this my matrix A. So maybe A inverse is this guy. How do I check? Well, I just need to take this thing and multiply it by the matrix A. You guys see that? So I'm going to take 0, 1, 1, 0, and I'm going to multiply by 1, 1, 0, 0, 1. And out of this, let's see, so I'm going to get this guy times that stuff gives me what? What do you get out of this thing? Are you guys doing pickup drops on for me? Are you doing column multiplication? What are you doing? This is boring when none of you talk. How about notice that this matrix is the identity matrix, right? So when you multiply something by it, you're going to get that thing back. Otherwise, you could do column multiplication or you could do pickups and drops on. I don't care. But you get here. Is this I? Is that the identity matrix right here?
No.
No. Damn it. Okay. So A inverse is not this thing because I know that if I multiply this thing on the left, I get something not the identity matrix. You guys see that process? Okay. So that didn't quite work. What do I need to multiply this thing by to get the identity matrix?
Itself?
Yeah. This is the identity matrix, right? So its inverse is the identity matrix itself. So this is a weird matrix where A inverse is A. You guys see that? Kind of with me? Maybe not. Okay. Let me consider the maybe matrix that Cody proposed, because actually that was my next example. Okay, so let's look at this one. What does this matrix do? If I multiply this by a vector xy, what do I get?
YX.
Good. Okay. So this thing seems to switch row 1 and row 2, right? This is a permutation matrix. So if you want to switch, if you switch row 1 and row 2, how do you get back to where you started? In other words, what do I do to yx to get back to xy?
The same thing?
Yeah, you need to switch them again. Right, so this matrix that Cody proposes has itself as an inverse. Now, this is two examples of matrices that are their own inverses. You guys see that? Do not get used to this behavior. It is not generally true that matrices are their own inverse. You guys all good with that? Let's just double check that quick. So, is the matrix 1, 2, 3, 4 its own inverse? How do I check? I need to take the matrix 1, 2, 3, 4 and multiply it by itself, right? Okay, so this first entry is going to be pick this thing up, twist it, and drop it on there. So you're going to get, let's see, 1 times 1 plus 2 times 3. Do I need to do any more computations to know that this is not the identity matrix? Why or why not, guys? Guys, anybody?
Doesn't the identity matrix need ones? So that's not one.
Perfect. That's not 1. And the identity matrix is 1s on the diagonals and 0s otherwise. Right? So having checked one entry, I know that this isn't the identity matrix. Now, wild fact, with 1 minute remaining, the inverse of the matrix 1, 2, 3, 4 is you need to switch two things. So the two things are the diagonal. So you switch those positions. You slap a minus sign on the anti-diagonal and multiply by 1 over the product of the diagonal. So 4 minus the product of the anti-diagonal, 6. This is a total cheater trick. I encourage you to memorize it because it makes your life hella easy. So notice that I divided by something here. So really what I did was I took the matrix A, B, C, D, right? And I said the inverse of a 2 by 2 matrix is 1 over AD minus BC. And then here I did D and A and minus B and minus C there. You guys all follow that pattern. It's switch and pop a minus sign on the anti-diagonal. Okay, now the question is, would this ever fail? When does this fail? Could that fail?
Zeros?
Yeah, if AD minus BC is 0. You guys see that? That's actually exactly the same thing you would get if you asked whether the columns or the rows were linearly dependent. You can fiddle it around a little bit. I encourage you to do that because I'm a little bit out of time. This number on the bottom here is so convenient that we give it a name. It's called the determinant. We're going to deal with it a bunch going forward. But for right now, I just want you to know that this 2x2 trick exists and that matrix inverses have to have this property that the product in both orders is the identity matrix. And they have to be square. Pretty good on that? We'll talk about why some more next time. Okay, let's call that a day. You can check this if you want. I actually encourage you to go check it quick. So do that multiplication. Make sure that you get the identity matrix from both sides. Doing the homework from that section is going to be a little bit challenging, but you guys got this, okay? So let me know when you get hung up, all right?